Okay, so once again I'm going to do a little bit of help for the homework. I'm going to try and do these one at a time. So in this video I'll do problem 5. So problem reads, suppose that x is an uncountable set and that x naught is a given point in x. Let the topology on denote the Fort topology on x. And the Fort topology is defined in the following way. The sets that are called open in this are either going to be these sorts of sets where x minus u is finite, in other words, just like the finite complement topology, or that given point x naught is not in u. And then the question asks two things. Show that for an uncountable set with the Fort topology, you have a Hausdorff space. So what do you need to show if you're going to show a Hausdorff space? Well, if I kind of let this be my x with the Fort topology, then it's Hausdorff if I can, for any 2 points, x and y, in x, I can find an open set that contains x and an open set that contains y, and the intersection of those open sets is the null set. So there are two cases. There's case 1, which is x and y are not x sub 0. In other words, there's a particular specified point in the Fort topology. That's this x naught. And if we choose 2 points, then one of them could be x naught and one of them could not be x naught, or neither of them could be x naught because it's an uncountable space, so there's lots of points. So the case, I would suggest doing this in 2 cases. First, where neither of them are x naught. And here's something to notice. Here's a set that contains x, does not contain x naught. So this set, that's a little x, not a big X, by the way. Maybe I should make my big X really big here. So this set is open. Similarly, little y, the set containing just that element y, doesn't contain, again, it doesn't contain x naught. So is also open. And I don't know, I probably don't have to write this. X intersect y is the null set. They don't intersect. So there's an open set that contains x and an open set that contains y, and they don't intersect. Now, the other case you have to do is case 2, where either x or y is x naught. In other words, you choose 2 points, one of them is x naught. Well, again, it's not particularly hard to do. If it doesn't contain x naught, then it has to have a finite complement. So consider this, just consider this set, which is big X minus y, and that certainly has a finite complement. and x naught is an element of, if I call this u, and u is open. And you can still use this set y, which is an open set that contains y, is open, and u intersect y is the null set. Now that's actually the easy one. Several people have already talked to me and they've gotten that one. The second part is the hard part. Now we want to show that it's not first countable, which is actually often a fairly hard thing to do. So it has to be true for all points, and in particular I'm going to consider the point x naught in x. And then I'm going to do this by contradiction. So suppose x with the finite complement topology, I should actually, or not finite complement topology, but the Fort topology, with the Fort topology, is first countable. So suppose it is first countable. What do you get if it's first countable then? There is, well, what I called in class a local basis, which is we have a u x naught I. We have this set such that x naught is in all of these, right? X naught is the point I chose to look at closely. If it's first countable, then in particular there's a set of open sets around this. And for any v such that x naught is in v, one of these suckers, there exists u, well, I'll use n, x naught, such that u n x naught is contained in v. Right? That's a local basis. So any open set that contains x naught, if it happens to be first countable, also has to contain one of these local open sets, part of this local basis. So I'm going to assume that's true and show that it leads to a contradiction, or at least I'm going to start this proof. And I've seen a few different ways to do this, so if you didn't do it this way, that's fine. So I claim, and you should verify this, that if I intersect all of these u sub I x naughts, since this is a Hausdorff space, the only thing that's in the intersection of all of these open basis, all of the sets in the local basis, is x naught. So if I intersect them all, I get x naught. And in particular, what that means is, since the only open sets that contain x naught, let's go back up to the definition of the Fort topology, the only open sets that contain x naught are those with a finite complement. In particular, all of these open sets have to have a finite complement. So you can get a contradiction here by noticing that if the intersection, and this is over the natural numbers, or the, and let's say I, an element of the natural numbers. So there's a countable number of these. Then what this implies is that there's a single point in this intersection, that shouldn't be a, yeah. And that should be the intersection over a bunch of sets, over a countable number of sets that are of this form, x minus, and I'll write this in not the best notation but evocative way, a finite number of elements now we use our De Morgan's laws to write this as, this is x, big X, minus a union, not a, keep mixing up my u's and my unions, but the union over I in n, in other words a union of a countable number of finite number of elements right? So that's just De Morgan's laws. And then we get this, well this is a countable set. So what this amounts to is an uncountable set minus a countable set. The union of countable sets is countable, that's where I get that from. And that's supposed to be equal to, well, according to our assumption, that's supposed to be equal to a single element. So finite. But if we take an uncountable set and we subtract off a countable set, then you don't have to know this from the past, I'm just telling you this. An uncountable set minus a countable set is always uncountable, so it can't be finite. So we get a contradiction. And I'll end this video with a pool of blood. And I'll try and make another video for the others here in a